take us in this array to the right of 73, how many days did it take us to find a new temperature that was greater than 73? Well, on the exact next day, we found 74, which is greater than 73. So it took us 1 day. So in the first position, we're going to return a 1. What about 74? How many days did it take us to find a new temperature that was greater than it? 75, 1 day later, right? Okay, for 75, how many days did it take us? 71 is not greater, 69 is not greater, 72 is not greater, but 76 is greater, and you can see that took about 4 days, right? So then we return a 4 in that position. Now, there are some temperatures that never have temperature greater than them. Look at these last two
可能性二，我就去挥发了。这个拽是什么？我就决定挥发了，让 index 这一杯结束的时间点就是拽。如果我就去挥发了，我有没有占用洗咖啡的机器？我没有占用。
You've done it! You've landed an on-site interview with Google. Congratulations! My fellow Googlers and I would like to share our tips and advice on how to prepare. In this video, we will cover communication and collaboration, creating algorithms and using data structures, writing clean and structured code, testing and error checking, and overall best practices.
Communication and collaboration are incredibly important in the work we do here at Google, and that's because it's key to how we approach developing and building our products. In your interview, it's important to demonstrate those qualities. Understanding a problem, designing a solution, and writing code are all valuable parts of the interview process. We want you to think out loud. We don't just want to see the final code, we want to understand how you arrived at it. Google is a collaborative workplace where projects are planned and executed by teams. Those teams have a mission to work together to solve big, often ambiguous problems, not just write code. And those problems can have multiple valid solutions. So, tell us your plan on how to solve these problems and be sure to ask questions. And remember, we're not looking for one specific answer. Some of the problems you'll encounter during your interview will be deliberately underspecified. We leave those questions open-ended because real engineering problems require you to dig deeper.
At Google, we deal with planet-scale data and compute systems every day. Simply identifying a solution isn't always enough. The code we write needs to be fast enough to respond to users and make efficient use of our resources. You should have a strong understanding of commonly used algorithms and data structures to do just that. When you're presented with a problem, it's probably a good idea to outline the algorithm and discuss it with your interviewer before you jump into the coding. It will give you an opportunity to refine and improve your solution collaboratively with your interviewer. Understanding the computational complexity of your solution is also important. Remember, you don't have to come up with the optimal solution up front. Iterating to improve your solution can be a valuable part of the process. You're also going to want to use appropriate algorithms and data structures. You should have a strong fundamental understanding of commonly used data structures like arrays, linked lists, stacks, and queues. You'll want to know sets, maps, trees, heaps, and graphs as well. It's also essential to know which algorithms tend to go along with each data structure. Algorithms that are used to solve Google problems typically include sorting, searching, and binary search. You should also be familiar with divide and conquer, dynamic programming and memorization, greedy algorithms, and recursion. And be sure to brush up on algorithms linked to specific data structures like graph traversal. You won't be expected to answer questions requiring some obscure and highly domain-specific algorithm. When you're working out the requirements of an algorithm, this could also be the perfect time to think of good test inputs.
At Google, developers may work across different platforms, but the foundational knowledge required to perform their job function is the same. Candidates will be expected to write idiomatic code in a programming language and style they are comfortable with. Common languages candidates choose to write code in includes C++, Java, Python, JavaScript, or Go. Choose the language you are comfortable with. We are evaluating you on conceptual understanding, and we know that if you are fluent in one
无所谓，
programming language,
没关系。Kotlin 就是谷歌的
also are not trying to
，Kotlin 当时就是谷歌好像也差不多19年左右才开始大面积用的。
with language trivia. So don't worry too much about memorization, syntax, or punctuation. We want the substance of your code to shine through.
Google's products and services are important for billions of people around the world. When we make changes, we need to be confident that we're not breaking important existing features. After you're finished coding in your interview, you'll want to run through at least 1 or 2 test cases to check your work. Good test inputs should exercise the boundary conditions in your inputs and your algorithm. Use simple and compact sample inputs first to ensure your code is correct. And lastly, you may also be asked to discuss malformed inputs and how your code handles them.
Now that you have the focus areas, here are some overall best practices to keep in mind for your actual interview day. We want to understand how you think, so it's important to explain your thought process during the interview. We're not only evaluating your technical ability, but also how you solve problems. Many questions will be deliberately open-ended to give us an idea of how you think. We'd encourage you to ask for clarification. And we all know that our first solution may not be the best one. So once you come up with an answer to a question, think about ways to improve upon it. Let your interviewer know what you're thinking. And lastly, practice on paper or whiteboard. You may have the option to use a computer and or whiteboard during your interview, so you'll want to make sure you practice for both possible options and that your code is easily readable if written.
And those are our tips to help you prepare for a coding interview at Google. If you have any questions about your upcoming interview, you can always reach out to your recruiter. We're here to help, and we look forward to seeing you at one of our offices around the world soon.
我好紧张呀！我现在刷题真的是越刷越没信心，我真的是。好难呀！看一下这个视频。
You've done it. You've landed an on-site interview with Google.
啊，这是刚刚看的呀。你看他说建议的读的东西吗 ？Coursera algorithm 这个 Princeton login it's Google 对，是的。我们看这个吧，普林斯顿的教授讲的，应该比那个讲的应该不比他差，好吧 ？To calendar， 这个也挺，我不知道看一下吧，好吧。这个总共多长时间啊？一共是我想知道这个一共是多长时间的课？1个小时48，2个小时，3个小时，4个小时，差不多5个小时吧。这是第一部分，还有第二部分？
Welcome. I'm Bob Sedgwick, Professor of Computer Science at Princeton. This is our online course, Algorithms, developed by myself and Kevin Wayne here at Princeton. We're going to start with an overview, discussion of why you might want to study algorithms, and then a little bit of discussion about the resources that you need to take this course. So what is this course? It's an intermediate level survey course on algorithms. We're going to concentrate on programming and problem solving in the context of real applications. And our focus is going to be on two things: algorithms, which are methods for solving problems, and data structures, which store the information associated with the problem and go hands in hand with algorithms. These are the basic topics that we'll cover in Part 1 and Part 2 of the course. The first part is data types, sorting, and searching. We'll consider a number of data structures and algorithms that are basic to all the methods we consider, including stacks, queues, bags, and priority queues. Then we'll consider classic algorithms for sorting, putting things in order. That's quicksort, merge sort, heap sort, and radix sorts. And we'll consider classic methods for searching, including binary search trees, red-black binary search trees, and hash tables. The second part of the course is for more advanced algorithms, including graph algorithms, classic graph searching algorithms, minimum spanning tree, and shortest paths algorithms, algorithms for processing strings, including regular expressions and data compression, and then some advanced algorithms that make use of the basic algorithms that we developed earlier in the course. So why should one study algorithms? Well, their impact is very broad and far-reaching. From the internet to biology to commercial computing, computer graphics, security, multimedia, social networks, and scientific applications, algorithms are all around us. They're used for movies and video games, for particle collision simulation. They're used to study the genome and all manner of other applications. So that's one important reason to study algorithms. Their impact is broad and far-reaching. Algorithms are also interesting to study because they have ancient roots. The first algorithm we study goes back to 300 BC, dating at least to Euclid. The concept of an algorithm was formalized actually here at Princeton by Church and Turing in the 1930s. But most algorithms that we consider were discovered in recent decades. In fact, some were discovered by undergraduates in a course like this. And there's plenty of other algorithms waiting to be discovered by students like you. The main reason that people study algorithms is to be able to solve problems that could not otherwise be addressed. For example, in the first lecture, we're going to talk about the network connectivity problem, where the problem is, given a large set of items that are connected together pairwise, is there a way to get from one to another with a path through the connections? As you can see from this example, it's not clear whether or not there's such a path. We need a computer program to do it. In fact, we need an efficient algorithm to do it. In this case, the answer is that there is such a path. Another reason to study algorithms is for intellectual stimulation. Algorithms are very interesting objects to study. Don Knuth, who wrote several books on algorithms and was a pioneer in the field, said that an algorithm must be seen to be believed. You can't just think about an algorithm, you have to work with it. Another quote from Francis Sullivan says that great algorithms are the poetry of computation. Just like verse, they can be terse, elusive, dense, and even mysterious. But once unlocked, they cast a brilliant new light on some aspect of computing. Algorithms are interesting for intellectual stimulation. Another reason many people study algorithms, and I suspect many of you, is it's necessary to understand good algorithms, efficient algorithms, and good data structures in order to be a proficient programmer. Linus Torvalds, who created Linux, says that the difference between a bad programmer and a good one is whether he considers his code or his data structures more important. Bad programmers worry about the code. Good programmers worry about data structures and their relationships, and I might add, the algorithms that process them. Nicholas Wirth, another pioneer in computer science, wrote a famous book called Algorithms plus Data Structures equals Programs. Another reason nowadays to study algorithms is that they have become a common language for understanding nature. Algorithms are computational models, and algorithmic models are replacing mathematical models in scientific inquiry. In the 20th century, scientists developed mathematical models to try to understand natural phenomena. It soon became clear that those mathematical models were difficult to solve. It was difficult to create solutions to be able to test hypotheses against natural phenomena. So more and more and more nowadays, people are developing computational models where they attempt to simulate what might be happening in nature in order to try to better understand it. Algorithms play an extremely important role in this process, and we'll see some examples of this in this course. Another important reason is that if you know how to effectively use algorithms and data structures, you're going to have a much better chance at interviewing for a job in the technology industry than if you don't. So here's a bunch of reasons that I just went through for studying algorithms. Their impact's broad and far-reaching. They have old roots and present new opportunities. They allow us to solve problems that could not otherwise be addressed. You can use them for intellectual stimulation to become a proficient programmer. They might unlock the secrets of life in the universe, and they're good for fun and profit. In fact, a programmer might ask, why study anything else? Well, there's plenty of good reasons to study other things, but I'll submit there's no good reason not to study algorithms. So for this course, we have two resources that I want to talk about and make sure that people are familiar with before entering into the content. This is a publishing model that Kevin Wayne and I developed and have been using for many years, and we think it's a very effective way to support the kinds of lectures that we're going to be giving in this course. Down at the bottom, and it's optional for this course, we have a textbook. It's a traditional textbook that extensively covers the topics in the course. In fact, many more topics than we can present in lecture. And then supporting that textbook is free online material that we call the book site. You can go to the book site to see the lecture slides, but more important, there's code, there's exercises, there's a great deal of information there. In fact, maybe 10 times what's in the book, including a summary of the content. So during this course, you'll be referring to the book site frequently. while working online. People often ask about prerequisites. We're assuming that people who take this course know how to program, know the basics of loops, arrays, functions. They have some exposure to object-oriented programming and recursion. We use the Java language, but we don't dwell on details of Java. We mostly use it as an expository language. We do some math, but not advanced math. If you want to review the material that we think is prerequisite to the material in this course, you can do a quick review by looking at sections 1.1 and 1.2 of the book, either at the book site or in the textbook. If you want an in-depth review, we have a full textbook called An Introduction to Programming in Java, an Interdisciplinary Approach. There's a book site and a textbook as well. But the bottom line is you should be able to program. And the quick exercise to get ready is to write a Java program on your computer, perhaps using our programming model as described on the book site. We'll provide much more detailed information on that as we get into the assignments. You can use your own programming environment if you're comfortable with one, or you can download ours. We have instructions on the web about how to do that.
Coursera 呀，这本书吗？给你下下来吧。我在后面再登斗鱼，播到斗鱼上的，居然都听得到。有，但是没有研发。你能打开吗？这个连接？好的。是吗？还可以这样的。哪一个？哪里啊？这个吗？这个不是啊，这是电子书啊，就点不开。这是个 PDF 文件。真的就是，就跟我们解题讲的一模一样的。点不动的这个图片。
Today we're going to talk about the union find problem, a set of algorithms for solving the so-called dynamic connectivity problem. We'll look at two classic algorithms, quick find and quick union, and some applications and improvements of those algorithms. The subtext of today's lecture really is to go through the steps that we'll follow over and over again to develop a useful algorithm. The first step is to model the problem. Try to understand basically what are the main elements of the problem that needs to be solved. Then we'll find some algorithm to solve the problem. In many cases, the first algorithm we come up with would be fast enough, maybe fits in memory, and we'd go ahead and use it and be off and running. But in many other cases, maybe it's not fast enough, there's not enough memory. So what we do is try to figure out why, find a way to address whatever's causing that problem, find a new algorithm, and iterate until we're satisfied. This is a scientific approach to designing and analyzing algorithms, where we build mathematical models to try to understand what's going on, and then we do experiments to validate those models and help us improve things. So first we'll talk about the dynamic connectivity problem, the model of the problem for union find. So here's the idea. They're going to have a set of n objects. It doesn't really matter what they are. We're going to use the numbers 0 through n to model our objects. And then we have the idea of a connection between two objects. And we'll postulate that there's going to be a command that says connect two objects. Given two objects, provide a connection between them. And then the key part of the problem is the find query, or the connected query, which just asks, is there a path connecting the two objects? So for example, in this set of 10 objects, we've performed already a bunch of union commands, connecting 4 and 3, and 3 and 8, and 6 and 5, 9 and 4, and 2 and 1. And now we might have a connected query that says, is 0 connected to 7? Well, in this case, there's no connection, so we say no. But if we ask, is 8 connected to 9, we're going to say yes. Even though we don't have a direct connection between 8 and 9, there's a path from 8 to 3 to 4 to 9. So that's our problem, to be able to efficiently support these two commands for a given set of objects. Now let's say we add a union 5, 0. And so that creates a connection between 5 and 0. 7 and 2 creates a connection between 7 and 2. And 6 and 1 between 6 and 1. So now if we ask, are 0 connected to 7? Well, 1 and 0, we can do that too. That's a redundant connection. And now if we ask, is 0 connected to 7? We're going to answer yes. So that's our problem. Intermix union commands and connected queries. And we need to be able to efficiently support those commands for a large number of objects. So here's a much bigger example. And you can see that we're going to need efficient algorithms. First of all, you can see we're going to need a computer for this. It would take quite some time for a human to figure out whether there's a connection. In this case, there is a connection. Now, the algorithms that we're looking at today are not going to actually give the path connecting the two objects. It's just going to be able to answer the question, is there a path? In part 2 of the course, we'll consider algorithms that explicitly find paths. They're not as efficient as human find because they have more work to do. Now, applications of these algorithms involve objects of all types. These are used for digital photos where the objects are pixels. They're used for networks where the objects are computers. Social networks where it's people, or computer chips where it's circuit elements, or abstract things like variable names in a program, or elements in a mathematical set, or physical things like metallic sites in a composite system. So all different types of objects. But for programming, we're going to associate each object with a name, and we'll just name the objects with the number of integers from 0 to n minus 1. That's a very convenient initial starting point for our programs because we can use integers as an index into an array then, and then quickly access information relevant to each object. And it also just suppresses a lot of details that are not relevant to union find. In fact, to make this mapping from an object name to the integers 0 through n minus 1 is a fine application of a symbol table or searching algorithm, which is one of the things that we'll be studying later in this course, algorithms and data structures for solving that problem. Now the connections, well, we need a few abstract properties that these connections have to satisfy, and they're all quite natural and intuitive. So we assume that is connected to is an equivalence relation. That is, every object's connected to itself. It's symmetric. If P is connected to Q, then Q is connected to P. And it's transitive. If P is connected to Q and Q is connected to R, then P is connected to R. Now these properties are very intuitive, but it's worthwhile to state them explicitly and make sure that our algorithms maintain them. When we have an equivalence relation, a set of objects and connections divide into subsets called connected components. A connected component is a maximal set of objects that's mutually connected. For example, in this small example here, there's 3 connected components. One consisting of just object 0, the second one objects 1, 4, and 5, and third one the other 4 objects. And these components have the property that if any 2 objects in them are connected, and there's no object outside that's connected to those objects, it's connected components. Our algorithms will gain efficiency by maintaining connected components and using that knowledge to efficiently answer the query that they're presented with. Okay, so to implement the operations, we have the find query and the union command. And so we're going to maintain the connected components. The find is going to have to check if 2 objects are in the same component. And the union command is going to have to replace components containing 2 objects with their union. So for example, if we have these components and we get the command to connect 2 and 5, essentially we need to merge the connected components containing the one containing 2 with the one containing 5 to get a big connected component. So now we have only 2 connected components. All of that leads up to, in a programming world, to specifying a data type, which is simply a specification of the methods that we're going to want to implement in order to solve this problem. So in our typical Java model, what we'll do is create a class called UF that contains 2 methods, one to implement union, the other one to implement connected, which returns a Boolean. The constructor takes as argument the number of objects, so it can build data structures based on that number of objects. And we have to bear in mind, as we're building our algorithms, that both the number of objects can be huge, but also the number of operations. We can have a very large number of union and connected operations, and our algorithms are going to have to be efficient under those conditions. One of the practices that we'll follow often in this course is to check our API design before getting too far into dealing with the problem by building a client that is going to use the data type that we develop. So for this example, we've got a client that will read information from standard input. First, an integer, which is the number of objects that are going to be processed, and then a series of pairs of object names. And what the client does is first it'll read the integer from standard input and create a UF object. And then as long as standard input is not empty, it's going to read two integers from the input. And if they're not connected, then it'll connect them and print them out. If they are connected, it'll ignore them. So that's our test client, and that's a fine test client to make sure that any implementation does what we expect that it will. So that's the setup. We've described the operations we want to implement all the way down to code, and we have client code that we're going to have to be able to service with our implementations.
是一个是吧？我数了一下。哎呀，1、2、3、4啊，5、6、7、8、7、9一个，2、8、1、2、8、7、8、7、9、0、5、1、9。19、7、8、7、9一个，2、8、1、2、0、5、5、6、3、4，四个是吧？哈，7、8，哦，1、2、1、9，哦，这是一个，这是一个2、8，两个，4个呀。你看1、2、7、8、7、9、19，这些是一个。哦，那3个。看，哦，是的，好的。真的是。
Of an algorithm for solving the dynamic connectivity problem called quick find. Now we'll look at our first implementation of an algorithm for solving the dynamic connectivity problem called quick find. This is a so-called eager algorithm for solving connectivity problem. The data structure that we're going to use to support the algorithm is simply an integer array indexed by object. The interpretation is that two objects, P and Q, are connected if and only if their entries in the array are the same. So for example, in this example with our 10 objects, the ID array that describes the situation after 7 connections is illustrated The situation after 7 connections is illustrated in the middle of the slide. So that at this point, 0, 5, and 6 are all in the same connected component because they have the same array entry 0. 1, 2, and 7 all have entry 1, and 3, 4, 8, and 9 all have entry 8. So that representation shows that they're connected. And clearly that's going to support a quick implementation of the find operation. We just check the array entries to see if they're equal. Check if P and Q have the same ID. So 6 and 1 have different IDs. Shows that they're 1, 2, and 7 all have entry 1. And 3, 4, 8, and 9 all have entry 8. So that representation shows that they're connected. And clearly that's going to support a quick implementation of the find operation. We just check the array entries to see if they're equal. Check if P and Q have the same ID. So 6 and 1 have different IDs. 1 has ID 1, 6 has ID 0. They're not in the same connected component. Union is more difficult. In order to merge the components containing 2 given objects, we have to change all the entries whose ID is equal to one of them to the other one. And arbitrarily, we choose to change the ones that are the same as P to the ones that are the same as Q. So if we're going to union 6 and 1, then we have to change entries 0, 5, and 6, everybody in the same connected component as 6, from 0 to 1. And this is, as we'll see, this is a bit of a problem when we have a huge number of objects because there's a lot of values that can change. But still, it's easy to implement, so that'll be our starting point. So we'll start with a demo of how this works. So initially, we set up the ID array with each entry equal to its index. And so all that says is that all the objects are independent, they're in their own connected component. Now when we get a union operation, so say 4 is supposed to be union with 3, then we're going to change all entries whose ID is equal to the first ID to the second one. So in this case, we'll change the connect 3 and 4 means that we need to change the 4 to a 3. And we'll continue to do a few more so you'll get an idea of how it works. So 3 and 8 now. So to connect 3 and 8, now 3 and 4 have to be connected to 8, so both of those entries have to change to 8. Okay, so now what about 6 and 5? So again, we change the first one to match the second one. So to connect 6 and 5, we change the 6 to a 5. What about 9 and 4? So now we have to change to connect 9 and 4, we have to change 9's entry to be the same as 4's. So now we have 3, 4, 8, and 9 all have entries 8. They're all in the same connected component. 2 and 1 means that we connect 2 and 1 by changing the 2 to a 1. 8 and 9 are already connected. They have the same entries in the ID array, so that connected query, that find, says true, they're already connected. And 5 and 0 have different entries. They're not connected, so we'd return false in that case, not connected. And then if we want to connect 5 and 0, then as usual, we'll connect the entry corresponding to both 5 and 6 to 0. 7 and 2, union 7 and 2, that's an easy one. And union 6 and 1, so now there's 3 entries that have to get changed. All those zeros have to get changed to 1s. So that's a quick demo of quick find. Now next we'll look at the code for implementing that. Okay, with this concrete demo in mind, then moving to coding up this algorithm is pretty straightforward. Although it's an interesting programming exercise that a lot of us would get wrong the first time. So let's start with the constructor. Well, we have a private integer array, that's our ID array, that's the data structure that's going to support this implementation. The constructor has to create the array and then go through and set the value corresponding to each index I to I. That's straightforward. The find operation or connected operation, that's the easy one. This is the quick find algorithm. So it simply takes its 2 arguments, P and Q, and checks whether their ID entries are equal and returns that value. If they're equal, it returns true. If they're not equal, it returns false. The more complicated operation to implement is union. And there we find first the ID corresponding with the first argument, and then the ID corresponding to the second argument. And then we go through the whole array and looking for the entries whose IDs are equal to the ID of the first argument and set those to the ID of the second argument. That's a pretty straightforward implementation. And I mentioned that a lot of us would get us wrong. The mistake we might make is to put ID of P here rather than first picking out that value. You can think about the implications of that. That's an insidious bug. So that's a fine implementation of quick find. Now the next thing is to decide how effective or efficient that algorithm is going to be. And we'll talk in some detail about how to do that, but for this it's sufficient to just think about the number of times the code has to access the array. As we saw when doing the implementation, both the initialize and the union operations involve a for loop that go through the entire array. So they have to touch in a constant proportional to n times they have to touch an array entry. Find operation is quick. It just has to a constant number of times check array entries. And this is problematic because the union operation is too expensive. In particular, if you just have n union commands on n objects, which is not unreasonable, they're either connected or not, then that'll take quadratic time, n squared time. And one of the themes that we'll go through over and over in this course is that quadratic time is much too slow, and we can't accept quadratic time algorithms for large problems. The reason is they don't scale. As computers get faster, bigger, quadratic algorithms actually get slower. And let's just talk roughly about what I mean by that. A very rough standard, say for now, is that people have computers that can run billions of operations per second, and they have billions of entries in main memory. So that means that you could touch everything in the main memory in about a second. That's kind of an amazing fact that this rough standard is really held for 50 or 60 years. The computers get bigger, but they get faster. So to touch everything in the memory is going to take a few seconds. And that was true when computers only had a few thousand words of memory, and it's true now that they have billions or more. So let's accept that as what computers are like. Now, what that means is that with that huge memory, we can address huge problems. So we could have billions of objects and hope to do billions of union commands on them. But the problem with that quick find algorithm is that that would take 10 to the 18th operations, or say array accesses, or touching memory. And if you do the math, that works out to 30 some years of computer time. Obviously not practical to address such a problem on today's computer. And the reason is, and the problem is, that quadratic algorithms don't scale with technology. You might have a new computer that's 10 times as fast, but you can address a problem that's 10 times as big. And with a quadratic algorithm, when you do that, it's going to be 10 times as slow. That's the kind of situation we're going to try to avoid by developing more efficient algorithms for solving problems like this. So quick find is too slow for huge problems. So how are we going to do better? Our first attempt is an alternative called quick union. This is a so-called lazy approach to algorithm design, where we try to avoid doing work until we have to. It uses the same data structure, our array ID with size n, but now it has a different interpretation. We're going to think of that array as representing a set of trees, it's called a forest, as depicted at right. So each entry in the array is going to contain a reference to its parent in the tree. So for example, 3's parent is 4, 4's parent is 9, so 3's entry is 4, and 4's entry is 9 in the array. Now, each entry in the array has associated with it a root. That's the root of its tree. Elements that are all by themselves in their own connected component point to themselves, so 1 points to itself, but also 9 points to itself. It's the root of the tree containing 2, 4, and 3. So from this data structure, we can associate with each item a root, which is representative, say, of its connected component. So that's a root of 3 is 9, going up that root. Now, once we can calculate these roots, then we can implement the find operation just by checking whether the two items that we're supposed to check whether they're connected, whether they have the same root. That's equivalent to saying, are they in the same connected component? So that's some work going to find the roots of each item, but the union operation is very easy. To merge components containing two different items, two items that are in different components, all we do is set the ID of P's root to the ID of Q's root. That's what make P's tree point to Q. So in this case, we would change the entry of 9 to be 6 to merge 3 and 5, the components containing 3 and 5. And with just changing one value in the array, we get the two large components merged together. That's the quick union algorithm, because the union operation only involves changing one entry in the array. Find operation requires a little more work. So let's look at the implementation, a demo of that one in operation first. So again, we start out the same way, but now the ID array entry really means that every one of these things is a little tree with one, take the root, 3. So now 4's, the root of the tree containing 4 is 8, and the root of the tree containing 9 is 9, and so we make 9 a child of 8. 2 and 1, that's an easy one. Now if we get our 8 and 9 connected, we just check do they have the same root, and they both have the same root 8, and so they're connected. 5 and 4, 4's root is 8, 5's root is 5, they're different, they're not connected. 5 and 0, 5 goes to be a child of 0. 7 and 2, 7 goes to be a child of 2's root, which is 1. 6 and 1, 6's root is 0, 1's its own root, so 0 becomes a child of 1. Each one of these union operations just involves changing one entry in the array. And finally, 7 and 3. So 7's root is 1, 3's root is 8, 1 becomes a child of 8. Okay, now we have one connected component with all the items together. All right, so now let's look at the code for implementing quick union. The constructor is the same as the other one. We create the array and then set each element to be its own root. Now we have a private method that implements this process of finding the root by chasing parent pointers until we get to the point where I is equal to ID of I. And if it's not equal, we just move I up one level in the tree, set I equals ID of I, and return it. So starting at any node, you just follow ID equals ID of I until they're equal, and then you're at a root. And that's a private method that we can use to implement the find operation or the connected operation. You just find the root of P and the root of Q, and if you check if they're equal. And then the union operation is simply find the two roots and then set the ID of the first one to be the second one. Actually, less code than for quick find. No for loops. There's this one while loop that we have to worry about a little bit, but that's a quick and elegant implementation of code to solve the dynamic connectivity problem called quick union. So now we're going to have to look at can this code be effective for large problems. Unfortunately, quick union is faster, but it's also too slow. It's a little different kind of too slow than for quick find. There's times when it could be fast, but there's also times when it could be too slow. And the defect for quick union is that the trees can get too tall, which would mean that the find operation would be too expensive. You could wind up with a long skinny tree of each object just pointing to a next, and then to do a find operation for object at the bottom would involve going all the way through the tree, involving n array accesses just to do the find operation. And that's going to be too slow if you have a lot of operations. Avoid putting the large is to commutativity problems. So how are we going to find algorithms, both of which are easy to implement, but simply can't support huge dynamic commutativity problems. So how are we going to do better? That's what we'll look at next. A very effective improvement is called weighting, and it might have occurred to you while we were looking at these algorithms. The idea is to, when implementing the quick union algorithm, take steps to avoid having tall trees. If you've got a large tree and a small tree to combine together, what you want to try to do is avoid putting the large tree lower. That's going to lead to long, tall trees. And there's a relatively easy way to do that. What we'll do is we'll keep track of the number of objects in each tree, and then we'll maintain balance by always making sure that we link the root of the smaller tree to the root of the larger tree. So we avoid this first situation here where we put the larger tree lower. In the weighted algorithm, we always put the smaller tree lower. Let's see how we implement that. Let's see a demo first. Okay, so again, we start out in our normal starting position where everybody's in their own tree. When there's only 2 items to link, it works the same way as before. But now when we have 8 to merge with 4 and 3, we put the 8 as the child, no matter which order the arguments came, because it's the smaller tree. So 6 and 5 doesn't matter, whichever one goes down doesn't matter. 9 and 4. So now 9's the small one, 4's the big one, so 9's going to be the one that goes down below. 2 and 1. 5 and 0. So now 5 and 0, 5's in the bigger tree, so 0 goes below. 7 and 2. 2's in the bigger tree, so 7 goes below. 6 and 1. They're in equal size trees. And 7 and 3, 3's in the smaller tree, so it goes below. So the weighted algorithm always makes sure that the smaller tree goes below. And again, we wind up with a single tree representing all the objects, but this time we have some guarantee that no item is too far from the root, and we'll talk about that explicitly in a second. So here's an example that shows the effect of doing the weighted quick union, where we always put the smaller tree down below for the same set of union commands. This is with 100 sites and 88 union operations. You can see in the top, the big tree has some nodes a fair distance from the root. In the bottom, for the weighted algorithm, all the nodes are within distance 4 from the root. The average distance to the root is much, much lower. Let's look at the Java implementation, and then we'll look in more detail at that quantitative information. So we use the same data structure, except now we need an extra array for each item gives the number of objects in the tree rooted at that item that we'll maintain in the union operation. Find implementation is identical to for quick union. You're just checking whether the roots are equal. For the union implementation, we're going to modify the code to check the sizes and link the root of the smaller tree to the root of the larger tree in each case. And then after changing the ID link, we also change the size array. If we make ID I a child of j, then we have to increment the size of j's tree by the size of i's tree. Or if we do the other way around, then we have to increment the size of i's tree by the size of j's tree. So that's the full code in white for implementing quick union. So not very much code, but much, much better performance. In fact, we can analyze the running time mathematically and show that the find operation, it takes time proportional to how far down the trees are in the node, the nodes are in the tree, but we can show that it's guaranteed that the depth of any node in the tree is at most the logarithm to the base 2 of n. We use the notation LG always for logarithm to the base 2. And so for if n is 1,000, that's going to be 10. If n is a million, that's 20. If n is a billion, that's 30. It's a very small number compared to n. So let's look. It's guaranteed. You have to increment the size of i's tree by the size of j's tree. In distance 4, let's look at the Java implementation, and then we'll look in more. Now we need an extra array that for each item gives the number of objects in the tree rooted at that item that we'll maintain in the union operation. Find implementation is identical to for quick union. You're just checking whether the roots are equal. For the union implementation, we're going to modify the code to check the sizes and link the root of the smaller tree to the root of the larger tree in each case. And then after changing the ID link, we also change the size array. If we make ID I a child of j, then we have to increment the size of j's tree by the size of i's tree. Or if we do the other way around, then we have to increment the size of i's tree by the size of j's tree. So that's the full code in white for implementing quick union. So not very much code, but much, much better performance. In fact, we can analyze the running time mathematically and show that the find operation, it takes time proportional to how far down the trees are in the node, the nodes are in the tree, but we can show that it's guaranteed that the depth of any node in the tree is at most the logarithm to the base 2 of n. We use the notation LG always for logarithm to the base 2. And so for if n is 1,000, that's going to be 10. If n is a million, that's 20. If n is a billion, that's 30. It's a very small number compared to n. So let's look at the proof of that. We do some mathematical proofs in this course when they're critical, such as this one. And why is it true that the depth of any node x is at most log base 2 of n? Well, the key to understanding that is to take a look at exactly when does the depth of any node increase. When does it go down further in the tree? Well, the x's depth will increase by 1 when its tree, T1 in this diagram, is merged into some other tree, T2 in this diagram. Well, at that point, we said we'd only do that if the size of T2 was bigger than or equal to the size of T1. So when the depth of x increases, the size of its tree at least doubles. So that's the key, because that means that the size of the tree containing x can double at most log n times, because if you start with 1 and double log n times, you get n, and there's only n nodes in the tree. So that's a sketch of a proof that the depth of any node x is at most log base 2 of n, and that has profound impact on the performance of this algorithm. Now, instead of the initialization always takes time proportional to n, but now both the union and the connected or find operation takes time proportional to log base 2 of n, and that is an algorithm that scales. If n grows from a million to a billion, that cost goes from 20 to 30, which is quite acceptable. Now, this was very easy to implement, and we could stop, but usually what happens in the design of algorithms is now that we understand what it is that gains performance, we take a look and see, well, could we improve it even further? And in this case, it's very easy to improve it much more. And that's the idea of path compression. And this idea is that, well, when we're trying to find the root of the tree containing a given node, we're touching all the nodes on the path from that node to the root. While we're doing that, we might as well make each one of those just point to the root. There's no reason not to. So when we're trying to find the root of p, after we find it, we might as well just go back and make every node on that path just point to the root. That's going to be a constant extra cost. We went up the path once to find the root. Now we'll go up again to just flatten the tree out. And the reason would be no reason not to do that. We had one line of code to flatten the tree amazingly. Actually, to make a one line of code, we use a simple variant where we make every other node in the path point to its grandparent on the way up the tree. That's not quite as good as totally flattening. Actually, in practice, it actually is just about as good. So with one line of code, we can keep the trees almost completely flat. This algorithm people discovered rather early on after figuring out the weighting, and it turns out to be fascinating to analyze, quite beyond our scope, but mention this example to illustrate how even a simple algorithm can have interesting and complex analysis. And what was proved by Hopcroft and Ullman and Tarjan was that if you have n objects, any sequence of m union and find operations will touch the array at most a constant of n plus m log star n times. And a log star n is kind of a funny function. It's the number of times you have to take the log of n to get 1. It's called the iterated log function. And in the real world, it's best to think of that as a number less than 5, because log star of 2 to the 65536 power is 5. So that means that the running time of weighted quick union with path compression is going to be linear in the real world, and actually can be improved to even a more interesting function called the Ackermann function, which is even more slowly growing than log star. And another point about this is it seems this is so close to being linear, that is time proportional to n, instead of time proportional to n times a slowly growing function in n. Is there a simple algorithm that is linear? And people look for a long time for that, and actually it works out to be the case that we can prove that there is no such algorithm. So there's a lot of theory that goes behind the algorithms that we use, and it's important for us to know that theory, and that'll help us decide how to choose which algorithms we're going to use in practice and where to concentrate our effort in trying to find better algorithms. It's an amazing fact that was eventually proved by Fredman and Sachs that there is no linear time algorithm for the union find problem. But weighted quick reunion with path compression in practice is close enough that it's going to enable the solution of huge problems. So that's our summary for algorithms for solving the dynamic connectivity problem. With using weighted quick union and with path compression, we can solve problems that could not otherwise be addressed. For example, if you have a billion operations on a billion objects, I said before it might take 30 years, we can do it in 6 seconds. And what's most important to recognize about this is that it's the algorithm design that enables the solution of the problem. Faster computer wouldn't help much. You could spend millions on a supercomputer, and maybe you could get it done in 6 years instead of 30, or in 2 months. But with a fast algorithm, you can do it in seconds on your own PC.
Quick union by size 3和6，对吧？那就是0跟到8呀，0的0，这个，对吧？哒哒哒哒，连3到6对吧？3只有1层，6 2层。比如说我们要把这边记到这边去，比如说0的 parent 变成8，就是记到这边来，对吧？什么意思啊？问的是 which ID entry changes， 就是0的 parent 变成8呢，不是吗？Quick union by sides。对啊，就是0记到8呀，对吧？这个不是看数的啊，它不是看数的数量吗？右边是2个呀，左边都是1个，不是吧？哦，union by sides with union by height. The size of the tree. 还有 unit by size 跟 unit by height，还有 unit by size 了，这个 size。为什么会？为什么这个也可以 guarantee 的？为什么这个也是 log n 呀？那个是 size 吗？那个不是 height 的吗？哦，你这么一说，好像是，那就是8的这个了，number of nodes。挺后悔我大学没看这个。
All right, now that we've seen efficient implementations of algorithms that can solve the union find problem for huge problem instances, let's look to see how that might be applied. There's a huge number of applications of union find. We talked about dynamic connectivity in networks. There's many other examples in our computational infrastructure. Down at the bottom, one is important one is in image processing for understanding how to label areas in images. We'll see later Kruskal's minimum spanning tree algorithm, which is a graph processing algorithm which uses union find as a subroutine. There's algorithms in physics for understanding physical phenomena that we'll look at an example in many others on this list. So the one we're going to talk about now is called percolation. That's a model for many physical systems. I'll give an abstract model and then just talk briefly about how it applies to physical systems. So let's think of an n by n grid of squares that we call sites. And we'll say that each site is open, and that's white in the diagram, with probability p, or blocked, that's black in the diagram, with probability 1 minus p. And we define a system to, we say that a system is percolated if the top and the bottom are connected by open sites. So the system at the left, you can find a way to get from the top to the bottom through white squares. But the system on the right does not percolate. There's no way to get from the top to the bottom through white squares. So that's a model for many systems. You can think of, for electricity, you could think of a vacant site as being a conductor and a block site as being insulated. And so if there's a conductor from top to bottom, then the thing conducts electricity. Or you could think of it as water flowing through a porous substance of some kind, where a vacant site is just empty and a block site has got some material, and either the water flows through from top to bottom or not. Or you could think of a social network where it's people connected, and either there's a connection between two people or not, and is there a way to get from one group of people to another, communicating through that social network. That's just a few examples of the percolation model. So if we're talking about a randomized model where the sites are vacant with a given probability. And so it's pretty clear that if the probability that a site is vacant is low, as on the left, two examples on the left in this diagram, it's not going to percolate. There's not enough open sites for there to be a connection from the top to the bottom. If the probability is high and there's a lot of open sites, it definitely is going to percolate. There'll be lots of ways to get from the top to the bottom. But in the middle, when it's medium, it's questionable whether it percolates or not. So the scientific question, or the mathematical question from this model, is how do we know whether it's going to percolate or not? In this problem and in many similar problems, there's what's called a phase transition, which says that when it's low, it's not going to percolate. When it's high, it is going to percolate. And actually, the threshold between when it percolates and when it doesn't percolate is very sharp. And actually, there's a value as n gets large that if you're less than that value, it almost certainly will not percolate. If you're greater, it almost certainly will. The question is, what is that value? This is an example of a mathematical model where the problem is very well articulated. What's that threshold value? But nobody knows the solution to that mathematical problem. The only solution we have comes from a computational model where we run simulations to try to determine the value of that probability. And those simulations are only enabled by fast union find algorithms. That's our motivating example for why we might need fast union find algorithms. So let's look at that. So what we're going to run is called a so-called Monte Carlo simulation, where we initialize the whole grid to be blocked, all black, and then we randomly fill in open sites. And we keep going. Every time we add an open site, we check to see if it makes the system percolate. And we keep going until we get to a point where the system percolates. And we can show that the vacancy percentage at the time that it percolates is an estimate of this threshold value. So what we want to do is run this experiment millions of times, which we can do in a computer, as long as we can efficiently do the calculation of how it does a percolator. It's a Monte Carlo simulation, a computational problem that gives us a solution to this scientific problem where mathematical models nobody knows how to solve yet. So let's look in a little bit more detail of how we're going to use our dynamic connectivity model to do this. It's clear that we'll create an object corresponding to each site, and we'll give them a name from 0 to n squared minus 1 as indicated here. And then we'll connect them together if they're connected by open sites. So the percolation model on the left corresponds to the connection model on the right, according to what we've been doing. Now, you might say, well, what we want to do is check whether any site in the bottom row is connected to any site in the top row and use union find for that. Problem with that is that would be a brute force algorithm, would be quadratic right on the face of it, because it would have n squared calls to find, to check whether they're connected for each site on the top, not check each site on the bottom, much too slow. Instead, what we do is create a virtual site on the top and on the bottom, and then when we want to know whether this system percolates, we just check whether the virtual top site is connected to the virtual bottom site. So how do we model opening a new site? Well, to open a site, we just connect it to all its adjacent open sites. So that's a few calls to union, but that's easy to implement. And then with that simple relationship, we can use exactly the code that we developed to go ahead and run a simulation for this connectivity problem. And that's where we get the result that by running enough simulations for big enough n, that this percolation.
就是挺聪明的几个方法，就是你看这个地方，如果你要判断，它不就要判断最上面这一列有没有连到最下面这一列嘛，对吧？那你要怎么判断呢？如果你要做的话，就是你建一个 unit find， 对吧？这边把这个连起来，这4个连起来，这几个连起来，然后你怎么算？你就是判断。比如这个点有没有连到上面任何一个点，对吧？然后它建2个对，然后你只需要去检测这2个点就可以了。这是一个点，后面他还说了一个，也很重要的，就是这样，就是因为它是不断加入新的点嘛，那加入新的点怎么算呢？就是放进去之后。
When we want to know whether this system percolates, we just check whether the virtual top site is connected to the virtual bottom site. So how do we model opening a new site? Well, to open a site, we just connect it to all its adjacent open sites. So that's a few calls to union.
就加了一个，把它周围这几个加起来。
But that's easy to implement. And then with
什么？听不清。对。
Simple relationship, we can use exactly the code that we developed to go ahead and run a simulation for this connectivity problem. And that's where we get the result that by running enough simulations for big enough n, that this percolation threshold is about 0.592746. With this fast algorithm, we can get an accurate answer to the scientific question. If we use a slow union find algorithm, we won't be able to run it for very big problems, and we won't get a very accurate answer. So in summary, we took an important problem, the dynamic connectivity problem. We modeled the problem to try to understand precisely what kinds of data structures and algorithms we'd need to solve it. We saw a few easy algorithms for solving the problem and quickly saw that they were inadequate for addressing huge problems. But then we saw how to improve them to get efficient algorithms. And then it left us with applications that could not be solved without these efficient algorithms. All of this involves the scientific method for algorithm design, where we try to develop mathematical models that help us understand the properties of the algorithms that we're developing. And then we test those models through experimentation, enabling us to improve algorithms, iterating, developing better algorithms and more refined models until we get what we need to solve the practical problems that we have of interest. That's going to be the overall architecture for studying algorithms that we're going to use throughout the course.
还挺好的啊，就是像 Unify 他讲的就挺，我们全当是去美国留学，是的，看这个 opening one is percolation simulation, how many times is 3、4吧。我想去找点东西吃，然后去洗漱，然后再躺床上看一看吧，好吗？我去把这个下下来，睡。 来了呀！我的手机上先下起来，我们先看着，然后手机下起来。
Performance character, a scientific basis. Today we're going to do some math and some science. Not a lot, but we need to have a scientific basis for understanding the performance of our algorithms to properly deploy them in practice. So today we're going to talk about how to observe performance characteristics of algorithms. We're going to look at how to make mathematical models and how to classify algorithms according to the order of growth of their running time. We'll talk a bit about the theory of algorithms and also how to analyze memory usage. So to put this all in perspective, we're going to think about these issues from the point of view of different types of characters. So the first one is a programmer who needs to solve a problem and get it working and get it deployed. Second one is the client who wants to use whatever the program did to get the job done. Third one is a theoretician. That's somebody who really wants to understand what's going on. And the last one is kind of the team, this basic blocking and tackling sometimes necessary to get all these things done. So there's a little bit of each one of these in today's lecture. And actually, when you're a student, you have to think that you might be playing any or all of these roles someday. So it's pretty important to understand the different points of view. So the key that we'll focus on is running time. And actually, the idea of understanding the running time of a computation goes way back even to Babbage and probably before. Here's a quote from Babbage. As soon as an analytic engine exists, it will necessarily guide the future of the course of the science. Whenever any result is sought by its aid, the question will arise, by what course of calculation can these results be arrived at by the machine in the shortest time? If you look at Babbage's machine called the analytic engine, it's got a crank on it. And literally, the concern that Babbage had in knowing how long a computation would take is, how many times do we have to turn the crank? It's not that different in today's world. The crank may be something electronic that's happening a billion times a second, but still we're looking for how many times does some discrete operation have to be performed in order to get a computation done. So there's a lot of reasons to analyze algorithms. In the context of this course, we're mainly interested in performance prediction. We also want to compare the performance of different algorithms for the same task and to be able to provide some guarantees on how well they perform. Along with this is understanding some theoretical basis for how algorithms perform. But primarily, the practical reason that we want to be analyzing algorithms and understanding them is to avoid performance bugs. We want to have some confidence that our algorithm is going to complete the job in the amount of time that we think it will. And it's very, very frequent to see in today's computational infrastructure a situation where the client gets bad performance because the programmer did not understand the performance characteristics of the algorithm. And today's lecture is about trying to avoid that. Now, we're going to focus on...
什么？好呀。论文。哦，好的。